Sure.
Can you hand me the thing here?
Yeah.
All right, hi everybody. We're going to get started. So today we have our guest speaker, Bo Dai from Google. Bo finished his PhD at Georgia Tech, and he's currently a staff research scientist at Google, where he works on all sorts of questions, theoretical and practical, in regard to reinforcement learning. I'm a big fan of a lot of Bo's work on off-policy evaluation and offline RL. Although I'm going to learn about something new with representation-based reinforcement learning today, so I'm really looking forward to that, and hopefully you are too. So please take it away.
Thank you. Thanks, Sergey, for the introduction. Yeah, let me put it here. Yeah, actually, can you hear me now? Great. Actually, today we'll talk about the representation-based reinforcement learning. I would say this representation is a little bit vague in machine learning because so many people claim they are doing representation learning. For example, the Sinclair, they say they want to do the visual representation and so on and so forth. But today, this representation is very specific, saying I want to find a. Okay, okay, I will hold it. So today I will.
Put it on your lapel so it's facing upwards. And try that.
Is this working now? I don't think it's still. I think it's still not working. Yeah, I will hold it anyway. So today we're talking about a very specific representation, which is I want to find a representation such that I can represent the Q function specifically. I think we will see it later. Yeah, this is actually several papers together. It's a years-long effort on this direction. And I should thank to the major contributor for this work, which is Thompson from UT Austin and Tianjun from here, Berkeley, and Chen Jun, Sherry, Lisa, Lina, and Dale and Chaba. Okay. Okay, let's start. Today, actually, the outline of the talk is first of all, I want to point out questions in current reinforcement learning, which is actually there is a trade-off between modeling, planning, and exploration. But actually, we haven't treated these questions very seriously in literature. We will see it into the details several slides later. And later, I will use this representation-based reinforcement learning to provide a coherent solution for this to achieve a delicate balance between this trade-off. Say we don't need to waste any computation effort to, say, for example, we usually have very complicated model, but once we get there, it's difficult to get an optimal policy from the model. So that means you are wasting some effort in sample complexity to learn this model, and the computation cost to for achieve optimal policy here. So that's why I'm saying we want to use this representation-based reinforcement learning to provide a coherent solution, to consider it as a whole problem. Okay, before we dive into the problem there, let's first make some definition of notation. I think, I don't know, maybe this is already very familiar to everyone sitting here, but I just want to make sure the notation is consistent with my following slides. Say we have state space denoted as S, and action space denoted as A, and the reward function, which is a function from state and action to the real number, and the transition operator, which is the conditional distribution. Once I give you the state and action, you provide me the probability of next state, and of course, the initial state distribution. I have another component in the MDP, which is H or gamma. H means if it's finite horizon, it's just H steps, and if it's infinite horizon, the gamma stand, which is a discount scalar from 0 to 1. Okay, and now I have some definition of notation here, which is the value function V, and also the state action value function Q. Okay, I think we don't have any questions here. Okay. Oh, by the way, if you have any questions, just interrupt me. I'm very happy to answer. Great. Okay, let's see. There are two major categories of the reinforcement learning algorithm. One is model-free reinforcement learning. one of the representative algorithm in model free IO is Q-learning, which is highly depends on the dynamic programming via this Bellman recursion. Q equals to R plus gamma transition with future Q. Okay, with this relationship, actually, we can construct the TD update, and then we can introduce the nonlinear function, for example, neural network, into it, and we get the deep version of this TD update. And nowadays we call it deep Q-learning. So this is one representative algorithm. And another one is policy gradient. Okay, this is just a review of a brief review of what exists. Okay, that's from the idea that we can construct the object function with respect to pi, which is accumulate reward from the beginning to the end. And we calculate the gradient with respect to the parameter in policy, and we update it with for the policy with stochastic gradient here. And it's also have a lot of different variants like natural policy gradient and soft actor critic, so on and so forth. These two are the representative algorithm for model free IL. Let's see what's the problem of it. The benefit of this algorithm is that we can easily incorporate the nonlinear neural network into it. For example, as I mentioned in previous two slides. But there are some questions here. One is if I introduce highly nonlinear function approximator to the Q function or the policy function, there's no guarantee we can achieve the optimal solution. That means you are wasting a little bit of modeling effort while you need to pay for it when you introduce the complex, when you use that kind of complicated nonlinear function for planning. That's one problem. And another one is actually we don't have any idea how to capture the uncertainty of nonlinear model for exploration. That's what I mean. There is a trade-off between modeling and planning and exploration. Okay, this is the drawback of this existing model-free IL. Any questions here? Okay, let's see another category, which is model-based reinforcement learning. This is the basic algorithm for flow for the model-based reinforcement learning. The idea is that first I collect the data from some policy, and then I use this data to estimate the dynamic model and the reward. And once I get it, I will use some model predictive control to calculate the optimal policy from it, and then execute this policy to collect more data, and so on and so forth, until I eventually stop somewhere. Okay? Let's see the representative algorithm here. Actually, most of the algorithm here are invented by Professor Sagi. For example, the first one, the model ensemble trust regime policy optimization, and yeah, these are the state-of-the-art model-based reinforcement learning for current moment. And if you really want to see the benchmark for this one, you can go to this link to see it. Still, let's see what's the pros and cons for this deep model-based reinforcement learning. As I mentioned, there's still a trade-off between modeling, planning, and exploration. In modeling part, we can definitely use a complicated model to estimate this environment, but it leads to the situation that once the more complicated the model it is, the difficult you get the optimal policy from there. This is the difficulty from planning, and of course, it's still like in exploration. Also, we don't have any idea how to capture the uncertainty from it. So yeah, this is the part I mentioned that there's elephant in the room in IL, but we never seriously take it as a question, as a problem. Okay, this is another representative algorithm in model-based reinforcement, which is called linear quadratic reinforcement learning. I would say even in this case, we still met some problem in the trade-off. It's not achieving very good balance between these three, between the modeling, planning, and exploration. Why? Because in the modeling part, we only use linear model or quadratic model for reward and linear model for the dynamic. And this gives us the benefit that learning problem actually is very easy. And also the planning, as we can see here, is convex optimization. And we can definitely get the global optimal for this algorithm. But let's see what happened. Yeah, we lost the flexibility to achieve, to model the real problem. We actually solve a wrong problem here. So, and here is the thing I want to emphasize. There is a trade-off between modeling, exploration, and planning. And the nature question is whether we can get a practical algorithm with rigorous theoretical guarantee to achieve balance between these three things. That's why we want to propose this representation-based reinforcement learning, where we use model-based reinforcement learning to get some, I think, arbitrary. Let me overclaim it a little bit. Arbitrary nonlinear model-based reinforcement learning model to capture the dynamic, and I can also achieve relatively global optimal for the planning and exploration. Okay, and before I dive into how I achieve here, any questions? For the, oh great. Yeah, good questions. The questions is why I say the exploration is difficult in nonlinear model. It is because for exploration, basically we need to estimate the uncertainty of my current model. And to be honest, in theoretical part, we only can provide a rigorous uncertainty estimation for linear model. And beyond linear, we don't have any computational efficient way to, or computational tractable way to estimate uncertainty. So that gives a difficulty for exploration. Is it?
By that you mean estimate uncertainty way that is guaranteed to work every time.
Yeah, roughly you can understand in this way. Yeah.
You want a hacked estimate uncertainty.
Yeah, definitely, definitely. Yeah, if you can. That's why I say theoretically we don't have such kind of way to get it. Uh-huh. Yeah, if we can estimate the uncertainty, yes, we can get the exploration works well. But the question is, the problem is we cannot. Yeah, but definitely you can use some ensemble as the model ensemble TRPO, but just not the rigorous way to capture the uncertainty. So it gives you the difficulty for exploration. Okay, any more questions? Okay, now let me start with vanilla nonlinear control model. Okay, compared to the linear quadratic regulator, this is replacing the quadratic reward function with arbitrary reward function, and I replace the linear dynamic model with the arbitrary nonlinear dynamic model, but just with a little bit of restriction, which is the noise is Gaussian. Okay, this is as a starting point. And yeah, this is difficult to solve for planning, which means for achieving the optimal policy here. So how I deal with it? Actually, let's first formulate the MDP formulation for this nonlinear dynamic model, which is I rewrite the dynamic as a transition operator. This is Gaussian, so it's not difficult to rewrite the transition operator here. And looking into this actually brings us to a very, very interesting factorization, which is I can decouple this transition operator with rewrite it into an inner product between two functions as kf times ks prime. here is inner product of two Gaussian to get the final exponential Gaussian part. Okay, although it's infinite dimension, but let's conceptually understand this is a infinite feature here. Okay, and of course with the random feature decomposition, which is also proposed by Benrat, we can rewrite it as expectation of this random feature here, phi function. Okay, once we get this decomposition, let's see what happened. So I can rewrite the transition operator as the inner product between phi and the mu. The phi is my, let's look back into the slides. The phi actually is my KFSA, okay? The mu actually is my KS prime. I just rewrite a little bit. And also I make an assumption saying my reward function is also representable by QSA linearly, okay? Once I achieve here, and remember the definition of value function here, what we can achieve is here. Let's say integration v with t, we can use the factorization of t and rewrite it into a phi times the integration. This is important to represent my Q function. And the first line of the Q function is the Bellman relationship, okay? And then I plug my factorization into the T so that I can get the Q function is phi transposed with this big chunk of thing. But actually, this integration is a vector. So you really don't need to worry about it. It's just saying the Q function can be linearly represented by my phi. Essentially, this is saying if I can find this phi function, I can linearly represent my Q function in this function space. Okay, that means the planning part actually is very easy now. I can utilize this relationship saying to achieve a balance between modeling, planning, and exploration. How? In planning part, actually, what I need to do is just doing a planning in this linear space. Yeah, the algorithm here is like I calculate the Q function as the linear span in Q, in phi, and so on and so forth. Although I write this as a integration part, actually in practice we don't need to do that. We just use the linear square value iteration to estimate this big chunk thing as a vector. Okay, and I do this from backward, step by step. And eventually I get my Q function linearly in phi. So that means, roughly speaking, with this phi function, I can say I can solve the planning for arbitrary nonlinear function, dynamic. And any question? Sorry?
You have an infinite dimensional matrix for LSTD, right?
For current moment, yes. Yeah, for current moment.
Make sure I didn't miss anything.
Yeah. So
it's very easy as long as you can do infinite dimensional.
Yeah, exactly. For current moment, this is only conceptually kind of give you an idea how I can, if I can handle the infinite dimension phi, how I can get this planning part. So yeah, go ahead. Oh, actually, this is a good question. Here is only for illustration, but in practice, you can just augment the phi with R, one more dimension. So eventually, you definitely can represent the R function here. Go ahead. I wouldn't call it kernel trick, because kernel trick, this thing is already been dominated by another SVM thing, right? This is not a kernel trick. This is like more or less like a specific factorization use kernel. Okay.
Yeah, but the actual kernel trick is conspicuously not used, right?
Yeah.
You're actually unpacking the features
Yeah.
and using the features
Yeah.
themselves.
Any questions more? And then I need to come back to the questions raised by Professor Ski, which is phi here is infinite dimension. So how I can deal with it? Actually, I don't want. Actually, I hide it. I thought no one will arise these questions. The point is that hiding here, that the second line, which is random feature part. Usually it's infinite dimension because I need to sample omega from a Gaussian distribution. But actually, I can use Monte Carlo to approximate it. So eventually, I can reduce the from integration to a finite sum, and I just reduce this infinite dimension thing to a finite dimension. And I just need to work with this finite dimension here. Actually, there are very complicated theorem issue behind this, which is if I use infinite dimension, the Q function is realizable, which means I can represent exactly with this Q function with my infinite dimension feature. But if I use random feature, there will introduce some approximation error. And actually, we recently just finished the theoretical guarantee to quantify this approximation error. The good news is it's not introduce any Kursov dimension. So we can safely use it in practice. Okay, go ahead. Yeah, this is another question. I should say honestly, I don't know. I have no idea. It's bring me actually very subtle questions, which is seems like stochastic thing is easier than deterministic now, at least from this perspective. Uh, yeah, this is just a starting point for us to believe we can do linear representation for the benefits for planning. Yeah, and that's after this I will introduce some recent work beyond this part. Uh, yeah, another part I want to comment is that although I here use some Gaussian as a noise, but actually this can be generalized easily, which is you just introduce phi in front in the left hand side of this notation. So phi s goes to f plus some Gaussian, and then the noise is no longer Gaussian for s, right? Okay, so and now we see the benefits of planning using this linear representation. And in this paper, we didn't use UCB, so we still use the Thompson sampling for exploration. That means there are still some intractability for exploration capturing in F. But we will see how we handle this later. But for this moment, I just use the Thompson sampling, where I estimate a posterior of the dynamic F, and every time I just sample from this F for exploration, and the middle part is planning. So nothing fancy here. Is this part clear, or should I dive into the detail here?
Just to clarify, this is a mathematician's algorithm where you solve the entire optimal control problem every trial.
Okay, let me dive into detail here. You see the second blue line, which is find the optimal policy pi k on fk with algorithm 2, which this is algorithm 2. I use this planning for optimal policy here. And this whole algorithm actually is outer loop, which is I want to use this Thompson sampling for exploration, which means every time I sample one f from my posterior, and based on this f, I get my policy, optimal policy, and then use my policy to collect the data. And later, I use this collected data to update my posterior, and this is whole iteration and so on and so forth. So outer loop is for exploration, and the inner part finds the optimal policy, which is only for planning in my previous slides. This is the whole algorithm. Yeah, any questions here? Okay, great. Let's see. Yeah, as I mentioned, I want to find a theoretical solid algorithm, provable algorithm. This is how we get it. we can prove the regret of this algorithm, which is independent of the state and action, and it only depends on the complexity of the dynamic function and the square root of t order. And the proof is actually, I skip it because it's quite standard. It's quite standard. The novel part is just how we do the planning part. But if you have any interesting about this part, I can explain later. Okay. Now let's see how it performs in practice. We compared to the results provided by the benchmarking the model-based reinforcement learning. The star, the algorithm with star is all copied from the benchmark one, and we follow the protocol to compare our algorithm, which is called speed, and the deep successor feature. And as we can see here, at least we are better than the state-of-the-art model-based reinforcement learning. Okay, this is the results on logical part. Sure.
So what's the policy solver in this case? That step that said like find the policy?
Yeah, yeah.
Are you doing MPC, or are you actually like running this as a simulator and running a policy?
Actually, good questions. I find the posterior of my f, and because I need to estimate the posterior, actually I use long-driving dynamics to get a different variant of the dynamic there. And after I get the dynamic f, I use random feature to extract the feature. And upon that, I use the soft actor critic to get the optimum policy here.
And presumably each iteration you don't like rerun soft actor critic from scratch, you just like increase the policy.
Yes, I fix the feature for representing my Q function, and based on that, I extract my Q, update my Q, and then with that, I update my policy there. Yeah. Okay, I'm hesitant to show this one actually. After the previous comparison with model-based reinforcement learning, actually we are very happy because we beat all the state-of-the-art model-based reinforcement learning. But still, you can see from here, it's very difficult. Okay, I didn't show it. Let's see. For example, the ant ET is only 800. Let's see how SAC is. SAC can get 2,000. So that's why I didn't put it into one table. It's really embarrassing to say this is better than, it's worse than SAC. But we in previous method, actually we fixed the random feature. We didn't learn it. And here we use it as a regularization. And that's why we call the speed regulation version. And now with that, we can achieve comparable with the SAC, sometimes better. Yeah, actually, I pause here. After we propose this method, actually, we're a little bit disappointed because we hope we can get better results because we achieve the state of, achieve the balance between the modeling, planning, and exploration. But practice, it's not that case, so it's a little bit disappointing at that moment. And that's why we go to later algorithm. And before we go to later algorithm, let's see what we learned here. What we learned actually is linearization indeed sometimes works, at least provides us some promising direction to go further. And as we already see, there's still gap between the in the practical cases. After this comparison, we conjectured there are several reasons why we didn't achieve the optimal, we didn't achieve state-of-the-art performance compared to SAC. One is that ideally we should use infinite dimension feature, but actually we only have finite dimension because random feature. We believe there's some error introduced by this random feature introduced. And another one is we also use Thompson sampling. And Thompson sampling required me to get an accurate estimating of the posterior, but we didn't. We used long-driving dynamics sample to sample from this posterior. And I think there's also some error here. And also we use Gaussian noise, and practically maybe it's not Gaussian noise. So I think there are several reasons for this. So that's why we want to further improve it to avoid that kind of errors introduced by this approximation. Okay. Yeah, can we do it better? Okay, questions. Sorry, can you repeat the questions? Good questions. Yeah, actually, in practice, we just fix the number in my implementation. Yeah, we use a scalar to estimate this number. We didn't do a fancy estimation for this covariance matrix. Okay. Yeah, go ahead. Yeah, when I say approximation, here are several different level of approximation. One is I use F model. The parameterization of F will introduce some approximation error. I didn't consider it. Here, I mean, theoretically, as I mentioned, and also Professor Gi noticed that we should use infinite dimension of phi. But in practice, we cannot do that. So we use random feature to reduce it from infinite dimension to finite dimension. This is why we call it infinite dimension linear approximation. So that's another level of approximation error. And the second part is because posterior, we can also not able to get this posterior accurately. So we use longevity to sample. It's also get some approximation error there. So there are several different levels of approximation. Yes. We use in this paper we use Euler dimension. Euler dimension to measure it. Yeah. Yeah, this is a starting point. So definitely there are so many drawbacks we didn't satisfied with it. But I think we should starting from here to just give a high level idea, say how we start this kind of research. And yeah, indeed it's promising to inspire later algorithm. Okay. Any further questions? Okay, let's see what's next. Okay, that's because this three of drawback, we really want to say whether we can directly estimate this whether I can directly estimate this factorization as a model-based reinforcement learning. The answer is no, it's really difficult. Because the red part, if we really want to get this model, we need to make sure the satisfied constraint, the constraint satisfied, which means for arbitrary state and action, I need to say the integration of this is equal to 1 to ensure it is a probability. Okay. And of course, this constraint is really difficult to satisfy because it's infinite many constraint. And of course, we can say, okay, I switch from the previous model to this model, where I normalize it explicitly. Yeah, this is indeed introduce some benefits for computation, for estimating it. But the bad thing is when we want to represent the Q function, we need explicit estimate this partition function. And this part is difficult. Okay. So the partition function really it's not like sampling we can ignore the part. No, in representing Q, we need it explicitly. This is really bad. So how can we deal with it? Okay, I forgot to mention another condition to satisfy. This condition actually is a little bit weird at the first line, which is saying for arbitrary G, which is upper bounded by some function, some constant, I need to integrate with mu, which is bounded. Okay, this condition is a little bit weird, but don't worry. Actually, eventually, it is trying to calculate the complexity of Q function, because you see, the integration part shows up there as W, and we need to bound the size of W, ensure this Q function is easy to optimize, easy to learn. Okay, this condition is for that. This is a purely theoretical condition. We may first ignore it. Okay, let's see. Yeah, come back to the main theme. MLE for learning the factorization is really difficult. Let me skip this part. How can we do it? Actually, we propose 3 ways to learn it. Let's first see this way, which is using the contrastive loss. And if you're familiar with CPC, indeed this is a CPC, contrastive prediction coding. Yeah, in this part we can ignore the partition function, and we also show that this is consistent with MLE, which means once you have infinite negative sample, the solution for this one is for phi. The solution for this one for phi and mu, it will recover the MLE. Okay. Yes, it is biased. And to be honest, we tried very hard to calculate this bias, but we failed. It's yeah. So it's really difficult to calculate this bias. Yeah. Okay, this is one way. And this is second way, which is once we finish the NCE estimator, we go back to see what phi really is. If we look back into the transition representation, it is phi times mu. Indeed, it is SVD for transition operator T. So that means if I can just get SVD, the problem solved. So that's why we go to this SVD decomposition. But this SVD decomposition is not easy to optimize because there is expectation inside of square. We cannot use the stochastic gradient to optimize it. So, I have read a lot of paper about Fincher-Dual. So I apply Fincher-Dual again. So now it becomes very easy to optimize expectation outside of everything, and stochastic gradient optimize it. And the better thing is because this is doing maximization, it's no longer min max, it's max. Perfect. So this is our recent paper here, and yeah, this is our second try. Okay, before I dive into the third method, I should mention a little bit connection between this spectral view to the successor feature. Okay, it's everyone familiar with successor feature here. But anyway, it's a very classic representation proposed about 30 years ago, but still recently, many people are using it for reinforced learning. Essentially, the successor feature, although didn't propose in this way, but actually mathematically it is equivalent to do SVD for I minus gamma p pi inverse. Okay, and the p pi is the transition operator integrated with some pi. So and also other kind of spectral features are listed here, but all of them depends on p pi, which is not t. Actually, this introduced some bad effect, which is your feature always depends on the policy you use, and once it changed, your feature also changed. While the feature we learned is for t, which is invariant for arbitrary pi. And also, for success feature, there's no rigorous exploration proposed yet. But for our method, we will see later, we can do exploration. Okay, here is the second way to learn the linear representation as we want by SVD, variational formulation for SVD. And before I dive into the next method, any questions here? Okay.
Quick question. The proto value and the Krylov basis, that you didn't explain that. We're not supposed to understand it.
That's some. Okay, that's some. Yeah. These are some existing features also can interpret as factorization of the transition, some variant of transition operator. I just listed here. It's very old paper if you're diving into, but the first one, success feature, actually is still used in practice. Yeah. And okay, now let's see the latest work of along this line, which is we really built the connection between linear MDP, linear feature, to latent variable model. This is actually very straightforward. You see, we can always rewrite the transition operator as integration between p s prime given z and z given s and a. And we rewrite it into inner product in L2 space. Okay, now we have phi equal to pz given sa, and mu s prime equals to ps prime given given z. And we treat the because we can treat the pz given sa as the phi function, and we can represent my qsa with this pz given sa. So straightforward, right? And the benefits of this latent verbal representation is that we can use the elbow to optimize it. Okay. So this elbow derivation actually is follow the standard formulation. I divide, okay, first equation is MLE, and I divide a variational distribution and times a variational distribution, and they are equal. And then I use Jensen inequality to get this second line. Okay, now what I need to do is just optimize this Q and my PZ given as in SA, and also my P S prime given as given Z. So this connection between latent variable model and linear MDP actually is very interesting. To be honest, actually this is quite surprising. I don't know why people didn't realize it. Say so many people use the latent variable model to model the dynamic, but the correct way to use the latent variable model is after you solve the model, you need to use the PZ given SA to represent your Q function instead of just a sample Z from it to represent the Q function. This is a significant difference between the latent variable model as linear MDP and the existing model-based reinforcement learning use latent variable model. The final line here. This is significantly different. Okay, so until now, any questions about this latent variable model estimation? Okay, good. Seems either everyone is missing or it's clear, crystal clear. Yeah. Okay, now we have the algorithm framework. Every formulation, every criteria I mentioned before can be plugged into this framework. The only thing changed here is how we estimate the latent linear representation. So the framework, like I first collect data, and I use either NCE or SVD or elbow to estimate my phi SA. And then I calculate the UCB bonus based on the representation alert. Now you see I don't need to use the Thompson sampling anymore. I just use this UCB bonus for my Bellman recursion for planning. After I solve this Bellman recursion by least square VI or least square policy evaluation, and I get my policy. So I go back to the first step, collect data, and refine my model, so on and so forth. Okay, as I mentioned, as I promised, I can show it is the sample complexity of this algorithm, which is polynomial with respect to the dimension I used for the phi function, while it's independent of the size of the state. If you are sharp enough, there is still some dimension, still some dependence with respect to action. We are trying to handle it. Yeah, go ahead.
So there must be something in there that depends on some measure of the state.
It depends on the dimension d. D is the number of dimension of the phi. So.
And is there some assumption that dimension, like presumably you can't just like set it to 1. So there must be some other framework showing up that makes that says that your phi should be accurate.
No, actually, we rely on assumptions saying this d will represent your dynamic.
Oh, so you won't realize.
Yeah, it's realizable. Yeah. Yeah, it's realizable. Okay, next slide is showing how this algorithm performs. Actually, to be honest, these three algorithm performs quite similar. So we just list one of it, which is use SVD. We call it speeder. Yeah, it's better than previous speed one, and also this time I can very confident to show the model free in one table with model based in one table. So we can dominate both model based and model free for the state of the algorithm. Okay, this is the empirical study for Mojico. Oh, sure.
For the implementation, you actually do this with LSPI?
Yeah, we didn't use LSVI. We still use the policy evaluation first, and then do the actor critic.
I see. So you're not actually doing LSPI in practice.
No, no, no.
You're just doing the regular break.
Yeah.
Did you try LSPI?
We didn't. We first evaluate. It's still use stack. It's based on the previous speed. We just changed the object function. We no longer use.
So what you changed is the features and the acceleration bar.
Yeah, we just changed that.
Was there a reason why you didn't want to do the LSPI thing?
This time we need to handle the continual action for Mojico. We didn't. It's really difficult for me to get the max with the action here. So that's why we do this way. And also we based on the MBBL benchmark, so it's easy to implement in this way. Okay, here is some curve such that we apply our algorithm to DM control, and the blue one is ours. You can see besides the ultimate performance, our algorithm also converge faster. Okay, especially in this worker sparse, which is we gave the sparse reward to the environment. Okay, I think before I list this part, any questions about this this method? And now, basically, I just want to claim that, as I mentioned before, there is a trade-off between the modeling, planning, and exploration. And now that we can safely say with this linear representation, we can achieve a delicate balance between the three things. Okay, any questions? Yeah, I think it's just because sometimes one or two seed just fail. Yeah, yeah. For this early stop. Sorry. Yeah, if you consider various, yes, I agree. Yeah, but I just say it's comparable. Sometimes it's better. Yeah. Okay. So if no, then this is another byproduct of this method actually, which is we notice there's a relationship between Q function and the policy, which is I can always construct a policy from current Q function. And now recall that our Q function can be linearly represented by my phi basis. So that means essentially I find another representation of skills by this phi. So this to evaluate how this skills learned, we follow the protocol of the offline skill learning and compare it to some state of the algorithm like OPA and skilled and also the trail. And I would say this algorithm is comparable with this specific designed for skill discovery algorithm. Okay, sure.
So concretely, what you're doing here is you are using the individual phis as skills and then learning like a high-level policy on them?
Yes, exactly. I use this.
Could you say a few more words about how that works?
Okay, great. After I learned this phi function, okay, I learned another policy which is condition phi, which is like pi a given s and phi sa. So I use this kind of stuff to to compose my downstream policy construction. So that's what I used here. Okay, I think this is the final slides, which I want to emphasize that linearization enable IL for nonlinear model to achieve the delicate balance, as I mentioned always in this talk, for flexible modeling, efficient planning, and efficient exploration. Of course, this is only the first several steps along this line. For example, we still have a lot of things to do. Is there any other better way to estimate this phi function? And also, I only do very little step about offline to online. How can we use online data to further improve this phi based on the offline learned component? And also, definitely, I didn't go to POMDP yet, which is more practical than MDP, because in practice we only have the image and the video. We don't observe all the state and action. So these are some listed directions as I can image for current moment to further work on. But definitely other kind of direction is also possible. Yeah. So yeah, I think this is for reference about what I talked today. The first one is about the random feature part, and second one is the NCE one, and third one, the fourth one is SVD and the latent variable model. And I think this is end of my talk. Any questions?